Hello, I'm Professor Dr. Salah Lotfi from the Polymer Chemistry Department at the National Center for Radiation Research and Technology, Cairo, Egypt. Today, I want to share with you the exciting conclusions from our latest research published in Polymer Bulletin.
I'm Professor Dr. Manal Fawzi Abu Talib from the Chemistry Department, College of Science and Humanities, Prince Satam bin Abdul Aziz University, and also a proud member of the National Center for Radiation Research and Technology in Cairo.
Let's talk about pollution, a major challenge facing our planet. Fortunately, adsorption swoops in as a superhero, offering sustainable solutions for environmental remediation. Today we're diving into the fascinating world of surfaces and what sticks to them. Ever wondered how charcoal filters water or how those little silica gel packets keep your new shoes dry? It's all thanks to a phenomenon called adsorption. Adsorption is like molecular Velcro. It's all about how molecules in a gas or liquid stick to the surface of a solid material. The Langmuir model makes a few assumptions to keep things simple. It assumes that all adsorption sites on the surface are equal, and that once a molecule occupies a site, no other molecule can join the party at that location. Tiny drug carriers like miniature submarines designed to deliver medications directly to specific cells or tissues in the body. 9. Beyond the basics. Exploring other isotherm models. Hey there, science fans. Today we're diving into the fascinating world of surfaces and what sticks to them. Ever wondered how charcoal filters water or how those little silica gel packets keep your new shoes dry? It's all thanks to a phenomenon called adsorption. Adsorption is like molecular Velcro. It's all about how molecules in a gas or liquid stick to the surface of a solid material. Think of it like this. Imagine a dance floor, our surface, and a bunch of eager dancers, our molecules. Some dancers prefer clinging to the edges, while others might venture further out. Now, how do we measure this molecular dance party? Enter adsorption isotherms. These handy graphs show us how much stuff sticks to a surface at a specific temperature, depending on the concentration of our dancers in the surrounding environment. In simple terms, an adsorption isotherm is like a report card for surfaces, telling us how good they are at attracting and holding on to specific molecules. Pretty cool, right? Let's meet our first contestant in the isotherm world, the Langmuir isotherm. Imagined by the brilliant Irving Langmuir, this model describes adsorption as a neat and orderly process. Imagine molecules lining up in a single layer on a perfectly smooth surface, each molecule finding its designated spot. The Langmuir model makes a few assumptions to keep things simple. It assumes that all adsorption sites on the surface are equal, and that once a molecule occupies a site, no other molecule can join the party at that location. This model is represented by a simple equation that's easy to plot on a graph. The graph helps us determine the maximum amount of stuff that can stick to the surface, which is super useful in various applications. Think of it like parking spaces in a parking lot. If all spaces are the same size and only one car can park in each spot, the Langmuir model helps us figure out how many cars the lot can hold when it's full. Now let's get real. In the real world, surfaces are rarely perfectly smooth and molecules don't always play by the rules. Enter the Freundlich isotherm, a model that embraces the chaos of real-life adsorption. Unlike Langmuir, the Freundlich isotherm isn't afraid of a little mess. It assumes that surfaces are heterogeneous, meaning they have a mix of different adsorption sites. Some spots might be more attractive to molecules, while others are less inviting. Moreover, the Freundlich model allows for multilayer adsorption. Molecules can pile on top of each other, creating a molecular tower of power. This makes it more suitable for describing adsorption on rough or porous surfaces. Think of it like packing a suitcase. You can neatly fold clothes and arrange them in a single layer, Langmuir, or you can stuff everything in, creating multiple layers of clothes, shoes, and souvenirs, Freundlich. So, which isotherm reigns supreme? Well, it all depends on the specific situation. The Langmuir model, with its assumptions of a uniform surface and monolayer coverage, shines when dealing with adsorption on smooth, homogeneous surfaces at low concentrations. On the other hand, the Freundlich model, embracing heterogeneity and multilayer adsorption, takes the crown when describing adsorption on complex, real-world surfaces, especially at higher concentrations. Imagine trying to model the adsorption of gas molecules onto activated carbon, a material with a highly porous structure. The Freundlich isotherm, with its ability to account for the diverse adsorption sites and multilayer coverage, would provide a more accurate representation of the process compared to the Langmuir model. It's like choosing the right tool for the job. You wouldn't use a hammer to tighten a screw, would you? Similarly, understanding the strengths and limitations of each isotherm model allows scientists to choose the best fit for their specific needs. Now that we've met our isotherm heroes, let's see them in action. Adsorption isotherms are more than just theoretical concepts. They are powerful tools used in countless industries to design and optimize various processes. One of the most common applications is in designing effective filtration systems. Whether it's purifying water, removing pollutants from air, or separating different components in a chemical mixture, understanding how molecules adsorb onto specific materials is crucial for developing efficient and targeted filtration technologies. Imagine designing a filter to remove a specific toxin from drinking water. By studying the adsorption isotherm of the toxin on different filter materials, engineers can identify the material with the highest affinity for the toxin, ensuring its effective removal from the water supply. From cleaning up our environment to developing new materials, adsorption isotherms play a vital role in shaping our world. Let's talk about pollution, a major challenge facing our planet. Fortunately, adsorption swoops in as a superhero, offering sustainable solutions for environmental remediation. Activated carbon, with its incredibly porous structure and high surface area, is a champion adsorbent, capable of removing various pollutants from water and air. Imagine it like a molecular sponge, soaking up harmful substances and trapping them within its pores. Heavy metals like lead and mercury, notorious for their toxicity, can contaminate water sources, posing serious health risks. Activated carbon filters, utilizing the power of adsorption, efficiently remove these heavy metals, providing safe and clean drinking water. In air purification systems, activated carbon filters combat volatile organic compounds, VOCs, those sneaky pollutants released from everyday products like paints, furniture, and cleaning supplies. By adsorbing these VOCs, activated carbon filters improve indoor air quality and protect our respiratory health. As we transition towards cleaner energy sources, finding efficient ways to store energy becomes crucial. And guess what? Adsorption is stepping up to the challenge, particularly in the development of advanced energy storage technologies like hydrogen storage. Hydrogen, with its high energy density and zero emission potential, holds immense promise as a clean fuel source. However, storing hydrogen safely and efficiently remains a key hurdle. Enter metal organic frameworks, MOFs, a new class of materials with incredibly high surface areas and tunable pore sizes. These MOFs act like molecular storage units, capable of adsorbing and storing large amounts of hydrogen within their porous structure. Imagine a tiny apartment building with countless rooms, pores, each capable of accommodating a hydrogen molecule. This high storage capacity, coupled with the reversible nature of adsorption, makes MOFs frontrunners in the quest for efficient hydrogen storage solutions. Section 8. Drug delivery on point adsorption's role in medicine. Now let's explore the fascinating world of medicine, where adsorption plays a crucial role in drug delivery systems, ensuring medications reach their targets effectively and safely. Imagine tiny drug carriers like miniature submarines designed to deliver medications directly to specific cells or tissues in the body. Adsorption plays a crucial role in loading these carriers with the drug molecules. By carefully selecting materials with specific surface properties, scientists can control the amount of drug adsorbed onto the carrier, ensuring a controlled and targeted release of the medication at the desired location. This targeted approach minimizes side effects and improves treatment efficacy, revolutionizing how we combat diseases. Section 9. Beyond the basics. Exploring other isotherm models. While Langmuir and Freundlich are the most famous duo in the isotherm world, there are other models out there, each with its own strengths and applications. The Temkin isotherm, for instance, considers the interactions between adsorbed molecules, assuming that the heat of adsorption decreases linearly with surface coverage. This model is particularly useful in describing adsorption on heterogeneous surfaces where molecule-molecule interactions play a significant role. The Dubinin-Radushkevich (DR) isotherm, on the other hand, is often used to describe adsorption in microporous materials, like activated carbon. It assumes a Gaussian distribution of adsorption energies, reflecting the diverse pore sizes and shapes found in these materials. These additional models provide a more comprehensive understanding of adsorption phenomena, allowing scientists to choose the most appropriate tool for their specific research or industrial application. Section 10. The future of adsorption, innovations and discoveries. The world of adsorption is constantly evolving, with scientists and engineers pushing the boundaries of this fascinating phenomenon to develop new materials and innovative technologies. Nanomaterials, with their incredibly high surface areas and unique properties, are opening up exciting possibilities in adsorption-based applications. Imagine tiny nanotubes acting as molecular filters, removing even the smallest impurities from water or air. Researchers are also exploring bio-inspired adsorption materials, mimicking the intricate designs found in nature. Imagine synthetic materials that can selectively capture and remove specific pollutants from the environment, just like how certain plants absorb heavy metals from contaminated soil. The future of adsorption is bright, with endless possibilities for addressing global challenges in healthcare, energy, and environmental sustainability. Section 11. Conclusion: the power of adsorption in our world. From the everyday act of brewing coffee to the development of life-saving medications, adsorption plays a fundamental role in shaping our world. Understanding the principles of adsorption, particularly the insights provided by isotherm models, allows us to harness this powerful phenomenon for countless applications. As we continue to explore the intricacies of surfaces and their interactions with molecules, we unlock new possibilities for innovation and discovery, paving the way for a cleaner, healthier, and more sustainable future. So the next time you see a silica gel packet or hear about water filtration, remember the incredible power of adsorption at work.